alternate title could also be Applications of Wald-Schmidt constants. So I think everyone who's here was here before, so maybe I don't have to summarize too much. There's nobody new, right? But let Z be a fat point subscheme it can be in n-dimensional projective space in general. And for notation, if J is a non-zero ideal, alpha J is just the least degree of an element of the ideal, a non-zero element of the ideal. And so in particular, I should write alpha of an ideal. But alpha of the subscheme, I'll just mean alpha of the ideal of the subscheme. So the Wald-Schmidt constant, so the Wald-Schmidt constant, you'll remember, is an invariant related to the subscheme. It's the limit, well, it's an infimum, in fact, of the ratios of the least degree of an element in M times the subscheme divided by M. But you can prove that this is a limit of these same ratios. So let me do an example. So let's blow up the points. And we get this, this rational variety. It has the basis of the divisor class group is just the same. So there's the linear class, the class of the pullback of a hyperplane. And then there is the blow-ups of the points. Just like before. And so let me define, here I have my Z. So E sub Z will just be the corresponding linear combination of the blow-ups of the points. And I want to look at a graph. So the horizontal axis will be minus E sub Z. I have minus, I guess minus E sub Z is here. And L will be here, pointing upward. And I can look at the convex hull. Of all ordered pairs Tm, such that TL minus Mz is the class of an effective divisor. So you can see as you increase L, it becomes more effective. You're deeper inside this cone. This is the cone of effective divisors for a slice of the divisor class group. I'm only looking at a two-dimensional slice. And as I go in this direction, it becomes more negative. So eventually I leave the effective cone. But the slope of this boundary is the Wald-Schmidt constant. So that's a more geometric way of thinking about the Wald-Schmidt constant. It tells you about slopes of the effective cone. So there are many. Here are just two of many interesting questions. So one of them I mentioned before. One of them was for P2. Compute alpha of z for what seems like the simplest possible case. Z is just the sum of the points, and the points are generic. And so when n equals 2, Nagata's conjecture says that the Wald-Schmidt constant should be the square root of the number of points. In higher dimensions, it'll be the nth root of the number of points. This is the square root because it's dimension 2. And it's open in all dimensions except 1. And in dimension 1, it's trivial. You can give it to your favorite, well, if you have a strong high school student, it's easy. Oh, and the second one, I wanted two. Two of many. Mathematicians don't count very well. So the second one, I want to give you a reference. It's not nearly as important as this one, but it's a question that we tried to answer in a paper that we just posted online, and so it's of current interest. Take the Klein configuration of 21 plus 28 equals 49 points. Yesterday, you might remember the Klein configuration consists of 21 lines, and the lines intersect at 49 points. 21 of them are points where 4 lines meet, and 28 of them are points where 3 lines meet, and there are no other points of intersection. So it's a 49-point configuration, and the problem is to compute the Wald-Schmidt constant. And so we have a conjecture. The conjecture is that the Wald-Schmidt constant is 6.5. We have pretty tight estimates. We were able to estimate it pretty closely, but we weren't able to compute it exactly. We were able to compute the Vmon exactly, and that's 13.5. But here is the reference if you're interested in looking at it. This is on the archive. 1609 08 648. And there are 7 authors, Thomas Bauer, Sandra DeRocco, me, Jack Huizinga. Jack actually did most of the work. And let's see, Alexandra Sicilianu, Thomas Gemberg. I think that's everybody. Anyway, you can check on the archive if you're interested. We use the Klein configuration is defined by a group action, and so we use the group action to enhance the computer calculations that we can do.
So is there some special reason why these special examples?
It's in 2014 we the same group that did this, there was a large overlap with the 2014 group that wrote a paper, and this was one of the questions that we had left over from that first paper, and so we were trying to see if we could push it further, and we were able to push some of it further. Part of the motivation was because I'll tell you what the connection is between the Wald-Schmidt constant and containment problems, but trying to understand the containment problems were part of the reason we wanted to know what alpha hat was. But it was also just partly a challenge. Could we do it?
If the points are more special, then it's below than square root to s?
Yes, that's right. Because the more special they are, typically the lower the degree is that you can find a curve that goes through the points.
So then it is constant, give upper semi-continuity, or I mean lower semi-continuity?
Yeah, there is a semi-continuity. It's not as simple. The problem here is that there are infinitely many things that can cause it to go up or go down.
But if you fix the number of points, then I mean you have only finite.
Except that you're looking at alpha hat with infinitely many multiplicities.
Oh yeah.
And so there are infinitely many. So it's not as simple as the usual semi-continuity. There's some sort of idea of if you avoid, for example, infinitely many proper closed sets, then it behaves the same on that stratum. So you have these. It may well be actually that you don't actually have to worry about that. So for example, on a Mori dream space, everything is finite. And so that isn't going to happen. But a priori, you might have to worry about infinitely many closed sets that you have to avoid to get the semi-continuous behavior. So it's complicated, and it's not completely understood when there are only finitely many conditions and when there are infinitely many. Part of it is related to bounded negativity. If bounded negativity is false, then there really could be infinitely many things that could cause trouble. Ooh, let's see. Okay, so part of the reason for mentioning these two things was just to remind you that the Wald-Schmidt constant is hard to compute. And so that is why there's motivation for finding estimates. So let's look at bounding the Wald-Schmidt constant. So the first bound was due to Wald-Schmidt. Wald-Schmidt and Skoda. So this is about 1978. And so what they prove is the following. They were looking at a subscheme of projective n space in general, but it was reduced. So they were just looking at a finite set of distinct points. And what they proved was the least degree of an element in the ideal of Z divided by the dimension is less than or equal to the Wald-Schmidt constant. And their proof, it used really heavy complex analysis. So I at one point tried to understand their proof, and it's just pages of integrating pluriharmonic functions of some kind, and so it's complicated. Now there are simple proofs now, but the simple proofs depend on big theorems, and so it looks like this is a fairly deep fact. In fact, Lazarsfeld Positivity book has a proof using multiplier ideals. And so you need a certain amount of background to understand the proof. The proof is not so easy, in my opinion, unless you know a lot about multiplier ideals. There's another proof, and this is the simplest proof. It uses ideal containments. And it also gives a much stronger result. So let me tell you what the ideal containment result is and what the proof is using that. So the proof depends on results of Ein, Lazarsfeld, and Smith, and Hochster and Hunicke. So these are two papers, one right after the other in Invenciones. And Ein, Lazarsfeld, and Smith get a weaker result, but their result motivated Hochster and Hunicke. They got a very clean general result. The techniques were different. The techniques here were multiplier ideals, and the techniques for Hochster and Hunicke, they used tight closure. But here's the theorem. So this is about 2000, maybe 2001, 2002. Their result is actually stronger than what I'm going to state, but it takes too long to explain how to, to make sense of everything. So I'll just stick to fat point subschemes. So Z is a fat point subscheme. Then the ideal containment is, I want to multiply Z by M plus N minus 1 times R. So the ideal of this multiple of Z is contained in the rth power of the ideal of M times Z. The left-hand side is the geometric side. This is what algebraic geometers would typically be interested in, because this is really the homogeneous components of this ideal are sections of line bundles on the blow-up. So this is very geometric. This really is algebraic. I mean, the ideal of M times Z, the homogeneous components are sections of line bundles. But when you take the rth power, then it's just some ideal. It's algebra.
So no n on the right side.
No. The problem is that when you take the exponent in, essentially this corresponds to the m. And so you take the exponent inside. When you take it inside, the ideal gets bigger. And so what you need to do is you need to increase something here to make the ideal small enough to fit inside the power of the ideal you have here. If you just take the Rn, if this is just M, it's false. So you need to make something bigger here to make the ideal smaller. And it turns out that this works. The simpler case, this is a refinement. The simpler case is this. Set M equals 1, then the M and the minus 1 cancel, and you get Rnz is contained in the rth power of the ideal of z. So you need to multiply by some number to get this thing small enough to fit inside this. And it turns out the dimension is enough. This is why this result is in invenciones. Nobody before this would have believed that the dimension would be enough to get this inside that. They assume that if the z was complicated, you might need larger and larger multiples to get it small enough to fit inside. And so the fact that the dimension works no matter what z is, and no matter what r is, that's very surprising. Or at least it was surprising when they came up with this. So this is the Ein, Lazarsfeld, Smith, Hochster, Hunicke result. It's really the Hochster, Hunicke version of the result that Ein, Lazarsfeld, and Smith came up with. Their result was more geometric, so it had additional conditions. The clean version here is due to Hochster and Hunicke. And now let's prove. So this proof is due to me and Roe from 2003. The archive citation for it is look in the math part of the archive, and the ID number is 0309 064 version 1, page 2. This is important. It never got published because, well, we didn't think it was that important. It turns out it is fairly important. We should have made more of an effort. At the time that we did this, it was just an offhand comment. And if you look at page 2, we make a comment saying that you can do this using this result, but we don't actually show how. But here's it eventually appeared in a paper that I wrote with Craig, but the original version was back in 2003. So here's how the proof goes. We have this ideal containment. So that means that this ideal is a bigger ideal, so its least degree element can't be bigger than the least degree, can't be bigger than the least degree element of this ideal. So that means that alpha of the rth power of this ideal is less than or equal to alpha of this ideal. Now, alpha is like a logarithm. This is a homogeneous ideal, and so the least degree element of a power of the ideal is in fact the power times the least degree element of the ideal. So I get this. And what I want to do now, I'm aiming to get the Wald-Schmidt constant. And to get the Wald-Schmidt constant, I have to normalize this by dividing by the multiple. So I'll divide by the multiple. On this side, the r's cancel. And here, I'll take a limit as r goes to infinity. And so this limit is the Wald-Schmidt constant. And so this is the proof. You have two choices. You can read pages of incomprehensible complex analysis. You can use multiplier ideals. Or you can assume this containment result and the proof is one line. Anyway, so this is this. I can't believe the proof can get much simpler than this. Lazarsfeld said he was surprised. He didn't realize you could prove this directly from this containment.
This proof very long. This theorem.
Oh, this theorem?
Yeah, you know.
Oh, this is now well known.
But it's very long.
Oh, yeah. So if you want a proof from scratch, you're right. And so that's what I was saying. You have to. Conceptually, this is a pretty simple proof. Conceptually, you have a containment, and the containment gives you the result. Proving the containment is actually not easy. There's no simple proof of the containment. But it used to be there was no simple proof of either one. And now this one has a simple proof, and this one we still need a simple proof of this. And in fact, Lazarsfeld, when he was writing this paper, he had a student, what's her name? She's at Mount Holyoke. All of a sudden, I can't think of it. Anyway, his student at the time, he asked her if she could try to prove this using classical methods. And no one knows how to prove this using classical methods. You have to use something like tight closure or multiplier ideals. It's not clear how to get a proof just using the usual commutative algebra and algebraic geometry. Okay, so there is one bound. This oh, there's my other page. Chudnovsky tried to improve the Wald-Schmidt-Skoda bound. And so this was in 1980, very shortly afterward. I assume by looking at examples, he decided the following might be true. And again, he's only looking at the reduced case. Their applications were to transcendence theory and number theory. So he conjectured that he started with the same thing, but he wanted to make the bound bigger. And what he decided was you can add something to the numerator to make the lower bound bigger. And then he gave a proof. He proved it for n equals 2. So if the points are in the plane, this is true. But in general, it's an open problem. So this is still open. And here is a sketch of Chudnovsky's proof. If you go to his paper, you won't see a proof. What you'll see is various examples and whatnot. And the examples give you an idea of what he was thinking. And based on what he was thinking, this is the proof that I think he had. But I don't know for sure because he didn't include a proof. In the same paper, he did something very similar for Nagata's conjecture. He claimed to have proved Nagata's conjecture in this paper. And he gives some brief details about how he thought the proof goes. But no one can make sense of it. At one point, I learned about this from Alain Naneau and Eckhard Wiefeg. And they couldn't figure out the proof either. And they contacted Chudnovsky to try to figure out what his proof was, but he never responded. And so it's not entirely, he's got a very severe illness. He's got myasthenia gravis, so it's a muscle wasting disease. He's in a wheelchair, he can barely move, and apparently he just doesn't respond to anything. It's too much effort. He does what he does and excludes everything else. So there's no way to find out from him what his proof was. Nobody believes the proof. But everything else in the paper seems to be true. I can verify everything else in the paper except the most important thing, which is the proof of of Nagata's conjecture. So here's the proof that Chudnovsky didn't give for this conjecture for n equals 2. So we have we have z, and we have the initial degree. So this means if you look at the ideal in the previous degree, the only thing there is 0. So what that means is each point of z imposes at most one condition. What we're doing is this is all contained inside the polynomial ring of P2, and we're only looking at the homogeneous forms of degree alpha z minus 1. So here we have a finite dimensional vector space. We're looking for the subspace of all forms that vanish at all of the points. And so you look at the subspace that vanishes at the first point. That drops the dimension by 1. And then you look at the subspace of forms that vanish at the first and the second points. That might drop it by 1, or it might leave it the same. If that second point is a base point of the system of polynomials that vanish at the first point, then the dimension does not drop. But at each step, the dimension drops either 1 or it stays the same. But eventually, the dimension drops all the way to 0. And this has dimension. Let's call this alpha. This has dimension. We're in dimension alpha minus 1. So that means it's got dimension alpha minus 1, choose 2. So that means there is a subset y of pi1 through pi alpha plus 1, choose 2 inside z of points where if you impose these points, the forms in this vector space that vanish at the first point, it drops by 1 dimension. It drops by another dimension at the second point. These points are all imposing independent conditions. And so what that means is the number of conditions imposed is the dimension of the space. So there are no forms that vanish at all of those points. Already with this subset of points of z, the conditions imposed have the result that you don't need all of the points of z to force alpha to be alpha of z. You can just take a subset of alpha plus 1, choose 2 points, and that already pushes the least degree up to alpha of z. And so the conditions that z imposes aren't necessarily independent. You may have too many points, but the conditions that y imposes are independent. So y imposes independent conditions on the vector space of forms of degree alpha minus 1. And so the next thing that you need to know, this is a lovely proof. Chudnovsky was brilliant. The next thing you need to know is that therefore the ideal of y in degree alpha, alpha of z, is base point free. If you look at the base point free off of y, the only base points are y. There are no additional base points. And the reason is the elements in the ideal of degree alpha generate the ideal. So if these are generators of the ideal, there can't be any additional base points because that base point would stay forever. But this ideal cuts out y exactly. So there can't be any base points. And why do they generate? Well, they generate because the fact that they impose independent conditions and there's nothing left in degree alpha minus 1, that means that the Castelnuovo-Mumford regularity is equal to the initial degree of the ideal. And all of the generators occur in the degree less than or equal to the regularity. If you don't like using this is sort of using a hammer that you don't need. If you know that the points impose independent conditions in degree alpha minus 1, there's an elementary argument, what Abiancar would call a high school algebra argument, which no high school student can actually do. But there's an elementary argument showing that there are no base points off of y. So this regularity thing is, it depends who you're talking to. If you're talking to commutative algebraists, they'll say, oh, sure, of course. And other people will say, all right, I'll take it on faith, but I don't understand. But this is a simple argument. You don't need the regularity. But that's an easy way. This is the magic word that works with commutative algebraists. Okay, so to finish the proof, there are no base points off y. Let's take an element in the ideal of m times z of degree alpha of m times z. So what I want to do is I want to get an estimate on the Wald-Schmidt constant. So I'll look in this. I want an estimate on alpha here. And then let G be an element of the ideal of Z. Well, actually, not of Z, but of Y. In the initial degree. Alpha of Z is the initial degree of the ideal of Y also. But here I need to make a choice. I want G to avoid, I don't want any component of G to be a component of F. But the ideal in that degree is base point free, so it's fixed component free. There are no fixed components. So I can always avoid any components that there might be in F by choosing G appropriately. So I want to choose G such that G has no factors in common with F. And that's where I'm using this fact here. It's base point free, so there are no common factors. I can avoid any common factor. So now use Bezout's theorem. How many points of intersection does F equals 0 and G equals 0 have? Well, the number of points of intersection is the degree of F times the degree of G. And what we know for sure is F vanishes on the points of Z, G vanishes on the points of Y. And so this product has to be at least as big as the number of points of Y And f vanishes at each of those points to order m. So I get m. And how many points in y are there? Well, we know exactly how many points there are. They're alpha plus 1 choose 2. So this expression is m times alpha plus 1 choose 2. And the degrees, we don't know the degree of f, but it's alpha of mz. And the degree of g is alpha of z. Well, this is m of alpha of z plus 1 times alpha of z. The alpha of z's cancel. And then I can divide by the m. And so alpha of mz divided by m is bounded below, oh, I forgot the 2. Is bounded below by alpha z plus 1 divided by 2. This depends on m, this doesn't, so I can take the limit and I get the Wald-Schmidt constant. So the Wald-Schmidt constant is bounded below by this.
So no s in this. So.
Oh, well, the s is this.
I see. S change.
Well, there are two s's. I mean, there's the s for y, which is this, and the s for z I didn't need. This proof of Chudnovsky's is, I think, beautiful and clever. It's very nice. But it depends on the fact that we're imposing only a single point, a condition from a single point. The points, if they had multiplicity, you'd be imposing many conditions at a time at each point, and you'd lose control. So this argument only works when z is reduced. It would be nice to come up with a proof where z doesn't have to be reduced, even in P2. And so in thinking about this, Craig and I tried to come up with an argument for why this might be true. And I was telling Craig about the results we were getting relating containments of ideals to problems like this. And Craig had the idea what kind of a containment would prove Chudnovsky's result. So this ended up being a conjecture in my paper with Craig. The question we wanted to address is, can containments prove the Chudnovsky conjecture? And so here's the conjecture that resulted. So the conjecture is let z be, it doesn't have to be reduced. It's only a conjecture. Nothing has to be anything in a conjecture. So I've got a fat point subscheme of projective space. Let M be the irrelevant ideal inside the coordinate ring of projective space. Then the conjecture is that the ideal of Rnz is contained in the irrelevant ideal raised to the r times n minus 1 times the ideal of z to the rth power. So this is very similar to the Ein, Lazarsfeld, Smith, Hochster, Hunicke result. Their result doesn't have this. If this is true, this is an improvement on their result. because we're making the right-hand side smaller. But this is still open. There are no counterexamples and there are no proofs. Well, there are proofs in special cases. So we've been able to prove this in a range of cases, but we don't know how to prove it in general. But it does give us a stronger version of Chudnovsky. So the conjecture this conjecture of mine and Craig's implies the Chudnovsky conjecture. Actually, it implies Chudnovsky, a stronger version, because we don't require Z to be reduced. And so the proof is exactly the same as over there. We have the ideal containment, so we take alpha. The smaller ideal has the bigger alpha. But alpha is linear in multiplication, in ideal multiplication. And so this is equal to R times n minus 1 alpha of the irrelevant ideal plus R times alpha of the ideal of Z. And the irrelevant ideal has elements of degree 1. So now you divide by R times n. And the R's cancel. And so what you get is, here you take the limit as R goes to infinity. So you get the Wald-Schmidt constant of Z. And here all you have is you have alpha of Z plus n minus 1 divided by n. And so if this containment is correct, we get a proof of Chudnovsky, a stronger version, in fact. And this has withstood the test of time. It's now 6 years, and so far no one has found a counterexample. But nobody has found a proof either. And so the obvious things to do are to use either multiplier ideals or tight closure. But the multiplier ideals don't give as strong a result as tight closure. So the obvious thing to do is to use tight closure. However, my co-author is the world's expert on tight closure. I mean, he invented it, and he doesn't know how to do it using tight closure. So there's no way I'm going to come up with a tight closure proof if Craig can. That isn't my thing, tight closure. So what that suggests to me is tight closure maybe isn't the right idea for this. Either that or it is the right idea, but for some inexplicable reason, Craig doesn't see the idea, which is possible. But in any case, it seems most likely that a new idea might be needed to prove this conjecture.
So this theorem is the corollary of this conjecture, or previous this Schmidt, this theorem is the corollary of this, or?
Yes, if you could prove this, that would prove the Ein-Lazarsfeld-Smith result, the weaker one.
I see, weaker one.
I think this is, you can also, it's not hard to see what you need to do to get the a version of this that generalizes their stronger containment. And maybe that's also true. If so, then what that means is you can improve the Chudnovsky conjecture a little bit more. But we didn't include that in the paper. And then some other people included it in their paper. So, yeah, so if you can prove this, you can prove their containment result. But
I call the containment problem.
Yeah, so the containment problem is, let me talk about that in the last few minutes. The containment problem. For what M and R do we have the ideal of M times Z contained in the ideal of Z to the rth power? Given a fat point scheme. And so the result of Ein, Lazarsfeld, Smith, and Hochster and Hunicke, that implies if M divided by R is bigger than N, then that containment holds. And so there are a number of questions you can ask. This N is a universal bound. As long as you're working on projective N space, this gives you the containment. In fact, I didn't talk about this, but it gives you the containment for any homogeneous ideal, whether it's geometric like this or not. But then you have to define what you mean. This is known as a symbolic power, so you have to talk about what symbolic powers mean. But the mth symbolic power of any homogeneous ideal is contained in the rth power of the ideal if this ratio is bigger than n. So this is universal. But maybe something smaller is universal. Can some C less than n work? Is there a smaller C such that every ratio bigger than that smaller C gives you containment? Well, it turns out the answer is no. Examples show that nothing smaller than n can work. Well, in the containment conjecture of mine with Craig, what we did was we tried to improve the Ein, Lazarsfeld, Smith result by making the right-hand side of their containment bigger. Or smaller, smaller, by multiplying by an ideal. What you could also try to do is you could try to make the ideal on the left smaller and leave this alone. And so the first idea was, suppose we make n smaller. Does that work? And the answer is no. And so what about, instead of a multiplicative constant, what about instead of taking r times n times z, what about subtracting a little bit off of r times n? So that makes this coefficient a little smaller, which makes the ideal bigger. So by subtracting something, we're really subtracting n minus 1. We've made the ideal bigger. And could this still work? This is actually the most you could possibly subtract and have a hope of having a containment. Because if you subtract n off, there are counterexamples. So what about only subtracting n minus 1?
R or n in the first one?
Oh, I want... it doesn't really work to talk about a ratio here because I'm subtracting something off. So here, I want to change the M, and I'm just looking at this particular containment. This would be an improvement on the result of Hochster and Hunicke if it were true. And it turns out this is false over the complex numbers for n equals r equals 2. And an example, the counterexamples, every example of a line arrangement with no simple crossings gives a counterexample. And so the Klein, the Fermat, and the Wiemann. I should say all non-trivial line arrangements. If you look at the singularities, if the line arrangement has no simple crossings, those points give a counterexample. But only for n equals r equals 2. And so it's an open question. It turns out things are different in characteristic P. In characteristic P, there are additional counterexamples. But over the complex numbers, are there containment failures when n is bigger than 2 or r is bigger than 2, and there are none that are known? The problem is it isn't really well understood how to arrange hyperplanes in higher dimensions and get interesting configurations. I mean, it's anyway, there aren't any counterexamples at this point. The only counterexamples so far are in the plane, and they're relatively few. So all of the counterexamples over the complex numbers with n equals r equals 2 somehow involve line arrangements where the number of points where there are just 2 lines crossing is small. So an open problem is to understand, why is that true? Why can't you come up with points that don't come from a line arrangement somehow and get a counterexample? So to finish, let me just show you these examples here have no simple crossings. But there are examples where you have some simple crossings. And you can still get a counterexample. These are only defined over the complex numbers. The one I'm going to show you in just a second is defined over the rationals. And so the fact that it's the complex numbers isn't essential. You can even do it over the rationals. But this is the only example I know over the rationals. So it's a small enough crowd that I can sort it. It always has a pleasing symmetry. We don't know any examples that don't have a pleasing symmetry. So this example has 12 lines with 19 triple points, but it's got 9 double points. There are 2 at each vertex and then 1 in the middle. So there are 9 double points. The counterexample comes from taking the triple points and ignoring the double points. If there are too many double points, it won't work, but this works. So all you need to do, and here is how all of the arguments work. And this is where I'll stop. So all of the proofs follow the following line of argument. All the proofs use the following argument. Z equals the singular points of a line arrangement of multiplicity, the singular points of multiplicity greater than or equal to 3 of a line arrangement, where the number of points of multiplicity 2 is small. There is no definition of small. This is just intuition. There is no. So anyway, then what happens is F is the product of the lines. So in this example, F would be degree 12. You take the linear forms defining the lines and multiply them together. Because F is the lines itself, it vanishes to order 3 at each of the points. And that's what we're trying to do. Because we're looking at n equals r equals 2, what we're trying to show is that the 3 times z, that ideal is not contained in the square of the ideal of z. And so this implies that F is in the ideal of 3 times z, because it vanishes at each of the points of z to order at least 3. And then use a computer to check that F is not in the square of the ideal. So if you have an element in the ideal of 3z that's not in the ideal of the square, then you have a failure of containment. All of the proofs work like that. So when you're looking for examples, what people have been doing is nobody knows where to look if it's not a line arrangement. So they start with a line arrangement that has a lot of points of multiplicity more than 2. They take the ideal of the points of multiplicity more than 2. They look at the F that they get and they check to see whether or not F is in the square of the ideal. If it is in the square of the ideal, you still might have a failure of containment, but that, as far as I know, there aren't any examples where that happens. And if F is not in the square of the ideal, then you have a failure of containment and you're done. It would be nice to understand whether this is the only way. It's not quite the only way. My graduate student actually showed that suppose you have a finite map of P2 to P2. Then pull back the ideal of a counterexample with this finite map. Then you get another counterexample. Take the inverse image of Z under a finite morphism of projective space to itself. Then you get additional counterexamples by pullback. You could argue, well, those don't come from a line arrangement. But my argument is they do come from a line arrangement, because you have to start with a counterexample, and they all come from line arrangements. You pull it back. That isn't a line arrangement example, but it came from one originally. And so right now there's no known way to avoid line arrangements and get counterexamples. Well, I think I'll stop here.